In this video, we'll be looking at the mathematical forms of representing AC signals. As you can see here, we have three forms of representing AC signal. The first one is the trigonometric form, and we can see the expression in this formula here. The second one is the polar form. You can see the expression here, and the third one is geonotation form. In this video, I'm going to be showing you with example how you can convert from one form to the other, and how we can see this trigonometric form as the major way of computing AC signals. So let's look at this example here. This example says we should express 5 at an angle of 53.1 degree in geonotation. We can see from here that this expression is in polar form. You can see that this is the impedance and is given as R, which is the magnitude, and this angle is the phase or the direction. So in order to move this expression from polar form to geonotation, the first thing we're going to take note is we're going to first of all look at the angle, and the phase here is 53.1 degree. Very quickly, I'll just take your mind to how we have our coordinate, where we have so take it to the way we used to measure the quadrants. If you can remember vividly, quadrants can be measured in the anti-clockwise direction. So from here to here is 90 degrees, from here to here is another 90, making it 180 to 17, and so on and so forth. So in order to map out the phase, we are looking at 53.1 degree. From here is 0 to 90, so our 53 should be within this area. And then that is the direction. So from there we can measure our magnitude. And in this case, the magnitude R is 5. So from here to here. So, and of course, these are Y, these are S as X. So from here we can see this is the magnitude, and we saw that magnitude here is 5. So let's assume that it is 5 at this point. So let's trace it to our S axis, trace it to our Y axis. So we don't know the value here, we don't know the value here, but we have an angle at 53.1 degrees. So next thing we're going to do now is to look for the relationship between our hypotenuse and our x. So from Pythagoras we can see, from our trigonometric ratio we can see that the relationship here between hypotenuse and the adjacent. From our trigonometric functions, we can see that the relationship between our hypotenuse and adjacent is cos. So from there, we can easily say that cos theta is the same thing as adjacent all over hypotenuse. So our adjacent here is our x. So x all over the hypotenuse is the value for our angle, our magnitude here. So we can as well write this as what? Cos 53.1 is equal to s over 5, which is the same thing as s being equal to 5 plus 53.1. And that as well can be, we can get out using our calculator. So if I type this out, I should have so our value here is 3. So in the same vein, we can get the value for y here, and the relationship between these is opposite and hypotenuse, which is sine. So we can say that as sine theta, sine theta in this case, which is sine 53.1, is the same thing as opposite over hypotenuse, which is the same thing as y into sine 53.1. And if this is typed out in our calculator, we can see that it's given us 5 sine 53.1, which gives us 3.99 approximately 4. So we can easily therefore represent this function now in G notation, and our Z becomes, for x, the value of x, which is 3, plus we bring our J and then put y, which is 4. And that will be the answer. So quickly we can verify this using this formula here. So what basically we are doing here is we can say that Z, we look at the value of R for here is 5 into what is our angle, plus 53.1 plus J sine 53.1. And if we do that, we can see that this is our function here and this is our function here, which inevitably give us 3 plus J4. And that'll be it for now. So I'll try one more example and we can move on to the next one. Expression 8 at an angle of minus 50 in G notation. Of course, we're going to represent them from our graph. This is our y axis and this is my s axis. So first thing is to look for the angle. We can see here we have minus 50. And remember, if I'm moving anti-clockwise, we count from 0 to 90. So if I'm moving clockwise, that means we're going the negative way. So therefore, our minus 50 can be seen from this angle. So if this is our R, then we can start forming our angles from here. And this, of course, is minus 50 degree. So here we can actually form our expressions for getting the value for our x and getting the value for our y. In the same vein, we are still working with adjacent and hypotenuse. So I can quickly substitute that into our equation, saying that what cos minus 50 is the same thing as x all over the value of r, which is 8. Okay, so our s can be gotten from multiplying this together, cos minus 50, and that we can use our calculator to get our expression. So expression is 8 into minus 50, which is equal to 5.14. Also, to get our y, which is this part of it, we can also form the expression using sine, which is sine of minus 50 is the same thing as y all over 8, and our y is equal to 8 sine minus 50, and we can get the value as 8 sine minus, we get the value as 8. So we now type out 8 sine minus 50 and get the value as minus 6.12. So our expression becomes, in G notation, becomes Z equals to the value of S is 5.14 plus. Now since we have minus here, this one becomes minus J 6.12. Now you may be wondering, how then can we move from G notation to polar form? This I'll show you in the next video. So you might be wondering, since we've tackled how to convert from polar form to G notation, so how then can we move from G notation back to polar form? We can do the same. We can use the same graph that we had when we were calculating from polar to G notation to find this expression. In this case, we already know that our S is equal to 10 and our Y is equal to 50. So I'll just draw the graph again. So in this case now, we know that what the value for our Y is 50 for this case, and the value of our S is say 10. So Now, let's say this is our expression. That means this is where our x meets. So here we don't know the angle. Alright, so I've drawn this out. This is value for our x, this is value for our y, and this happens to be a magnitude. And in this case, we don't know the value for theta, which is what we need to get in order to know the value of our fix here. So very quickly, the next thing you're going to look at now, since we know the value for this, which is our adjacent to be 10, I will know the value of our opposite to be 15. Now, what is the relationship between opposite and then adjacent? We can see that from tan. So from our tan, which is opposite over adjacent, we can get the value for our angle. So our angle can easily be gotten from what the tan inverse of opposite. What is our opposite? Which is our y in this case. So like I said, we can get our opposite. Our opposite here is our y, and our adjacent is our x, which is tan inverse of what? X, y, sorry, over x, which in this case is the tan inverse of 50 all over 10. That should give us the angle. So what is the tan inverse of 50 over 10? That's tan inverse of 5 will give us tan 5 will give us 98.69. Sorry, 78.69. So how then do we get the value for our resultant? Which is easy. We can see that from Pythagoras theorem, that which states that the square of the hypotenuse is equal to the sum of the square of the two other sides. So we can easily get the value of our r by saying that r square is the same thing as what? 10 square plus 50 square, which is the same thing as the root of 10 square plus 50 square. So our r can therefore be gotten by typing out the root 10 square plus 50 square, which will give us 50.99, which is approximately 51. So our expression therefore in polar form becomes 51 at an angle of 78.69. So that is how to move from G notation back to polar form.